All right, hey guys. So I'm Cooper. If you haven't met me, I'm one of your EP1 Test tutors, and this is just a video to help you prepare for Test 4. That should be this Friday, the 23rd. So this is just recording, and I know you can't ask questions while I'm going through this, so I will try to keep it relatively quick. And it's a recording, so you can pause, rewind, whatever, if you don't understand some stuff. But I would highly recommend you come to our in-person review on Thursday, the 22nd, the night before the test at 7 p.m. It'll be in the engineering hall in one of the big lecture halls. Please come. There's plenty of space for everyone who wants to come. And there you can ask like questions in person, and we can give you a lot better explanations to stuff that you might be wondering about. So we're going to go over, let me start the screen share. Let me try and show the right one this time. Test 7, or test 4, fall 17. Yes, so here we go. So like I said, this is from 2017, test 4. It has a lot of good stuff on it, and I'm not going to go through every single question. I will go through a lot of them, but throughout it, if you want to take screenshots, if you want to pause it and try and work on, I'll be like, hey, like try and work this out yourself, and then I might write like a quick answer, so you can like pause it, try and do it yourself, and then check it with mine. And I think that'll help you learn a lot better, especially because you can't ask questions in this format. So yeah, here you go. Please have patience with me. This is my first time creating a Zoom tutoring review, so we'll see how it goes. Yeah, so the first one, the figure shows a uniform metal plate. I'm not going to read all of it. Basically rank the following points according to the rotational inertia of the plate around a perpendicular axis through the embracers. All right, so the key to this is just the rotational inertia formula. I'm going to try and do my best to annotate here. One quick second. I need to stop this. Okay, sorry for that. I had to take a quick phone call, so let me reshare that screen. Okay, yeah, so as I was saying, the key to this is just the inertia equation, and also I am writing on a mouse, so it's like, it's just hard. So that is a sigma, let's see, right here, sigma m I r I squared. This is so bad, I'm so sorry. Okay, so basically you're just taking the different points and like plugging in the R's and the M's. And then what you get from that is you'll have C. Also, yeah, if you want to like do it, I recommend you pause it, and then I'll write the answer. So then you work through it, and then you can check the answer to see if you're right. So after you plug in your values, you should get A, or C is greater than A, and A is greater than B. And that should be your answer. All right, so going on to the next question. A cannonball, oh my gosh, okay, well, didn't know it wouldn't scroll with it, but so answer, and I'm going to just clear the annotations every time I move on to the next problem. So make sure you to pause and check as you go through. All right. I'll try and move it here. So, okay, a cannonball and a marble roll smoothly without slipping from rest down an incline. Is the cannonball's time to the bottom and translational kinetic energy at the bottom more or less than or the same as the marbles? So it gives you a little note here. The the rotational inertia of the center of mass of a solid sphere is 2mr squared over 5. So once you write this out, let's see, you just get, so you start with the marble at the top, so you have MGH, right? Again, I apologize for this handwriting, it's on a mouse. So you start with an MGH, it's all potential energy, and it's going to end up having this energy, right? So you're, this is just kinetic energy, and then you do plus your energy due to inertia, which is 1/2 cm W squared. So this is how you set it up. Again, I would just pause it and plug everything in. and see if you can get the right answer. So you plug your 2/5 mr squared into this ICM right here, and you solve, and what you end up getting is 7/10 the cm squared. So the time to the bottom basically is it's just going to remain the same because you're traveling the same y distance. So that's just going to be the same. The translational kinetic energy at the bottom is more or less than or the same as the marbles. So the kinetic energy, the marble's own energy is going to be this ICM squared. So you have 2/5. Oh, sorry, this is going to be, so when you solve for the VCM, that velocity is going to be the square root of 10/7 GH. So it's asking whether the translational kinetic energy is more or less than or equal to the marbles, and it's going to be more than. Gosh, takes all day. Because basically you're going to have more kinetic energy that's being produced, and that's going to be greater than like the internal inertial energy of the marble. So it's going to be same and more. I won't scroll so you can look at that. So in the figure, there's 3 forces are applied, F directs. So this is definitely hopefully going to be on the test. Again, I can't ever say what's on or on the test because I don't know. But this seems to be a very common question in the homework, and I've worked this problem a lot with people. So this is, you're just ranking the magnitudes of torques they create about P2, the greatest first. So F1, if you look at F1, F1 is coming out, if you can look at the screen. So we have P2 over here. It's on, basically, it's on X and Y axis. F1 is going out this way. It's pushing this way. That creates this 90-degree angle. So we know that torque is RF sine of theta, RF sine, oh my goodness, of theta. There we go. So, and then we'll definitely talk more about torque in the review. It's basically the rotational force about a point. So you know that this theta is going to be 90. It's going to have a coefficient of 1 to the RF. So we are assuming that all these R's are the same and all the F's are the same. So definitely F is going to be among the greatest that we have. But now let's go to F2. So as you see, if you look right here, this is 90 degrees from P2 to F2. So again, it's going to be sine of 90, which is going to be 1. So, given that the R and the F are the same, F1 is going to be equal to F2. This is definitely here, I guess I'll talk about that for a second. So F3, so we look at this, P2's here, this is going to be greater than 90. So we know that the sign of anything that is not 1 is going to be, less than or equal to 1, less than or equal to 1, equal to 1 here, sorry, less than or equal to 1, equal to 1 here at 90. So it's 1 here, and then it's 1 here on the z-axis. But once it starts going greater than 90, that sine of theta is going to be less than 1. You can plug it into a calculator if that doesn't make sense, but it's also how like sine works. It goes, and then it goes basically like 0 up to 1. 1 is the max, and it goes back down to 0 if you know your unit circle. So it is going, F1 and F2 are going to be equal, and they're both going to be greater than F3. If you have any questions about this, we'll definitely go over it in the review on Thursday. I've definitely seen a lot of these problems. I definitely understand this. Just remember, if it never gives you force, F or R, you're assuming that all these F's are the same and all the R's are the same. and it's all about the angle from which that force is acting on that point. All right, so in the previous question, consider point 3 for this point, in which direction is the torque from? All right, so for F1, when you think about it, if you're looking for the direction, torque is the cross of R and F. So if you have R coming this way and you have F going this way, your torque is going to be in the positive Z direction, right? Because you have negative, it's like the right-hand rule. You have a negative X plus a negative Z is going to equal or negative X Z, negative Z is going to equal positive X. And then you just use the right-hand rule for the rest of them. Positive X, positive Z, and positive Z for 3. And again, that's because the P2, the F2 and F3 are both acting on the same plane. So they are, and they're acting in the same like positive Y direction, or sorry, positive XY direction. So both of those are going to be positive Z. Okay, let me clear drawings and scroll. Okay, so initially, force F is the absence and disk M spins on its axis due to the presence of M, describe direction of angular displacement. So again, this is the right-hand rule. Pause it, try and work it out. I will write the answers, but we won't spend too much time on it. So again, pause, work it out, and I will write the answers now. So the angular displacement is into page. Again, just use into page, right? Use the right-hand rule. The angular velocity is also into the page, and the angular acceleration is also into the page. So now force F is applied. Describe the direction of the torque due to the force. So now the force is happening. So you have another force going this way, with this going that way. It's really hard to show on Zoom. But the force that is now applied, the direction of that is going to be out of the page. So out. Cool. If you have questions about that, again, please come to the review. I'll probably say that a million times before this is over. All right, so we go on to our first long answer. So this is a pretty common problem. I remember when I took it, I think we had something pretty similar on this topic on mine. So yeah, again, like if you remember from last unit, the conservation of energy, it also impacts this unit hugely. Only now we have to add in rotational inertia and the energy that is caused from that. So if you look at where we start, we're here, right? Nothing's moving. It doesn't say. So again, ball of radius mass, it starts from rest. So there's no initial force or velocity being added to it. So we start with mgh. That is all the energy that we have in the system, and it will all be equal to that. What this energy turns into is 1/2 mv squared, and this is just v center of mass. So this is your kinetic energy, plus your rotational energy due to inertia, which is 1/2 ICM angular velocity squared, w squared, or omega squared, as some say. So yeah, that's how you set it up. I would, again, pause, solve, and see if you can get it right. From the rest of this, it's pretty straightforward. It's rolling without slipping, so you don't need any friction or anything like that, or to add anything like that. And so once we plug in, so then also it is at an angle on this roof, so we have to make sure to account for our angle of gravity. So that this mgh is basically going to turn into mg L sine of theta, because we want that L for how long it actually goes down, and we want the sine of theta to take into account the angle. And then it's going to equal 1/2 mv squared, and it's going to equal, so this is just going down here, if that makes sense. And then this is going to become plus 1/2 1/2 times 2/5, because we are plugging in our I, as we see up here. So we're plugging in that 2/5 mr squared, Oh my goodness, that's an MR. That's MR squared. I'm so sorry. VCM squared. And I hope this makes sense. I'm trying to talk about it so you know what I'm saying. So basically, these R squareds will cancel out. These M's will cancel out because you can divide all terms by M. And then from that, we just solve. So we get our this to be equal to our GL sine of theta to be equal to 7 7/10 VCM squared. VCM squared. And again, that is equal to this. So when we are solving for this VCM squared, so we're going to move everything over, and we are going to get VCM. So we're just basically multiplying this side by 10/7. So we get 10/7. So all I did was just flip the sides. I didn't do anything fancy. 10/7 GL sine theta. Whoop. Okay. So again, I just divided this, or sorry, I multiplied this side by 10/7, and I have to multiply this side by 10/7. So this is just coming over here. That is all that's going on, and that was squared, so we need to square root that. Oh, okay. Please feel free to laugh at my mouse handwriting. I'm doing my absolute best. All right, so basically, so you plug in your G, you plug in your L, and you plug in your sine. And all those are given up here. And if you want to solve that really quick before I tell you the answer, okay, the answer should be, oh, my goodness, the answer should be 5.4 meters per second. And that's the answer. Cool. All right, cool. So I'll do this before I scroll. If the ball hits the ground 1 second after leaving the roof, determine the height of the roof. Okay, so this is basically, it sounds a little intimidating, but it is not bad. So we have our y and our y initial plus our v initial times yt. So this is going back to our like linear like velocity acceleration equations. Ay t squared. All right, so our ay, so we know that the acceleration that is going to be impacting it is gravity, right? So that's going to be 9.8. We know that our initial velocity is going to be equal to that velocity cm, our center of mass velocity, times sine of theta, again, due to the angle of the roof. And we have our height. Our height, sorry, that should be height. Yeah, so this is our height. All right, so our ending y is going to be 0 because we're falling all the way down to the ground. And we are going to get this 2.3 x1, x2 times 3 times 1 plus 1/2. And then we just plug in our 9.8. And then our t, which is 1 second. So that's 1 second squared. So then this is basically, we solve this for that. So that's where, so this boy is just plugging in right here. Once we plug that in, that's going to be equal to 2.3 meters per second. And that's where that 2.3 is coming from. And then again, that t is 1, so it's times 1. So our height is going to equal this value, which is 7.2 meters. So yeah, again, just going back to those initial linear velocity acceleration equations, this is one of them. It's just your initial y plus the velocity times your y times t plus 1/2 ay t squared. And again, the acceleration is just due to gravity, and that v is, we have to include sine of theta to account for the angle of the roof, and we should get 7.2 meters. So, all right. And I know I'm going fast, so please come to that review session if you have any more questions. But if this is helping, making sense to you, and you listen to this and you're like, oh, I got it, then you are good to go. You don't really need to come if you don't want to. But I would still, even if you feel confident, to still come, because when you feel confident, that's when you know something's wrong. Just kidding. Okay. Determine how far horizontally from the edge of the roof that the ball hits the ground. Okay, so again, we're just going back to those equations, those position equations. So we have our new x equals our x naught plus our velocity of x times time. So to get that initial velocity of x, we do, again, plug in that cm. But now we aren't taking into account the vertical portion of our velocity, we're taking into account the horizontal portion of our velocity, which when we plug that in, we get 5.4 cosine of 25. And then that is going to equal to 4.9. So then we plug that in, this final x is 0, or initial x is 0, I mean, and this is 4.9. So 0 plus 4.9, our answer is 4.9 meters. Cool. Cool. Yeah, so those look a little tricky at first, but when you're like, oh, hey, like, let's just like kind of pull back these old equations, they become a lot simpler. All right, so this one is tricky. We will go through this one. So this is all about inertia and rotational motion. Hang in there with me, and feel free to pause if you're ever confused or anything like that, but let's go through it. So the figure of this rigid assembly, the thin hoop, radius of that, length of that, the assemble's upright, but if we give it a slight nudge, it will rotate around horizontally in the plane of the rod and hoop through the lower end of the rod. Note that rotational inertia of a rod is that, and the hoop is that. So those will come into play. So basically, it's just asking, determine the expression for the rotational inertia of the hoop and the rod. So all we have to do is add the two rotational inertias of each. And luckily, we know just that. So rod plus hoop plus the I of the hoop. And all you have to do is plug in these formulas for that ICM. So again, this is going to be MM, and then so we know that our L is equal to 2R. So we can just plug in 2R for L. R squared. And again, this is this ML squared over 12 for the rod. And we are going to add the hoop, which is MR squared. So it should just be M R squared. All right, sorry. So that is just for the rod. Sorry, this is just for the rod. And then we have to add in the hoop. So plus ICM of the hoop. So basically you have to add in, because the equation is, so it's I rod. So I rod is actually going to equal ICM MR squared, right? So that's the equation. So we actually have to add in this MR squared here. So then we take the equation for the hoop, and then we add in, so this ML or this MR is actually going to be 9MR squared, and that comes from 3R squared. And that just becomes 9R squared here. And MR, 9MR squared. So when we plug everything in, you just cancel out, you plug in your R's, and you should end up with 10 5/6 MR squared. Again, I want you to do this little calculation in between because I don't think it'll help you very much if I just do the whole thing for you. Definitely try and get to this point. So then once you calculate 1056 mr squared, then you plug in your mass and your r, and you get 0.2524 meters. So again, this is the answer. Please solve this, work through it, understand it. If I just like go through and just do all the calculations, you're not going to learn much. All right, so given the center of mass of the tube and the rod is at 2r from the rotational axis. Use the principle of conservation of energy, so we're back to conservation of energy. Determine the angular speed as it passes through the upside down inverted orientation. So we have this at the beginning, we have mgh, right? So we have plus, and we also have that rotational inertial energy. So W naught squared, right? So the initial rotate, like so our initial W naught, and then that is going to equal this 1/2 IW squared, because at the bottom, so this right now has potential energy. Once it's at the bottom, it's all going to be this rotational energy. Luckily, so this W naught, we don't have any rotational motion before we start. So that W0 is going to equal 0, so we can just do that. So all we do is mgh equals I, or 1/2 IW squared. And we solve. So our W, once you basically, so we're solving for this W, once you manipulate the equation, you should end up with 2 mgh over I. Now remember, we already solved for our I, it's 0.24. That's the total rotational inertia. So make sure not to like solve for that again because you did all the work up here. So then yeah, you plug it in. So put 0.24 in for that. Plug in your mg and h, and you should get 7 radians per second. Boom. Answer. So yeah, as you're going through this, make sure to write down questions, take screenshots, whatever you need. These are the right answers. So if what I'm doing doesn't make sense to you, make sure you like read the question, look at how I'm setting it up, and go through and figure out how to do it for yourself. Because again, it is not going to help you if I just write all of this random stuff without you trying to solve it yourself. Okay, so determine the speed of the center of mass as it passes through the upside down orientation. So easy, we know that our velocity equals WR. We found our W, we have R. We plug in, but so then our actual R is going to be 2R because right up here it says, sorry, if you scroll back out, because I'm not going to scroll now, it says, given that the assembly is 2R from the rotational axis. So the R is going to equal 2 big R, if that makes sense. But the good thing is we know our R and we know our W, so you plug in 7 times 2 times 0.15, and you get 2.1 meters per second. Simple as that. All right, cool. Let's move on. All right, so this is probably the last question we'll be doing. This is a cockroach with mass rise at disk 6mr. I will write the answers for this, but I want you to try and do this on your own. It's pretty similar to what we've been doing. I'll write how you set it up, and I'll write the answer, but this is the last one we'll be going through in depth. Okay, so a disk of radius 0.1 meters and mass 100 kilogram. I'm sure you can read. 2 forces F1, F2, blah, 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 as a disk. So it's asking, determine the net torque acting on the disk. So again, we know that torque equals RF sine of theta, right? There we go. RF sine of theta. It says RF sine of theta. Okay. So our torque net is going to equal R F2 minus R F1 sine of theta. Okay, so a few things you're like, oh, why is sine of theta not here? Why are you subtracting? Let me explain. So F2, it is, again, 90 degrees from where we are rotating about, right? So that sine of theta is going to be sine of 90, which is 1. So we don't have to worry about sine of theta. And it's subtracting because one's going this way and one's going this way. So one's turning it this way and one's turning it the opposite way. So basically, we're just saying, okay, if this force is acting this way, this force is going to be acting the opposite way. So we have to subtract them. So it's really as simple as that. All you have to do is plug in your, so what they did was they took out R, which is 1, or 0.1, and we do F2, which is 1, minus F of 1, which is 2, sine of 45. Because you know that this is, that says theta is 45, and that is the angle from which it is acting about this point. Okay, sounds good. And so we are going to just solve that, and it actually ends up being negative 0.04 n. So then you basically can say, like, there's no, like, there's no necessarily negative way it's going. It's just the way you put it. So if you, but usually one counterclockwise or counterclockwise is usually positive. So what they have here is 0.4 Newton meters. They just made positive. But if you solve the other way, you would also get negative 0.06 Newton meters if you went about it and solved it a different way. Oh yeah, it says right here. So when you cross, your out of the page is positive, into the page is negative. So the cross of this torque is going to be out of the page if you use the right-hand rule. So it's going to say it's going to be positive torque. So determine the angular acceleration of alpha of the disk in units or radians per second. If the disk is rotating is the disk rotating clockwise or counterclockwise? So all you have to do is the net torque equals ICM alpha. That is just an equation you have to determine this. So you know that your rotational acceleration is going to be torque net over ICM. You basically just plug that in. So then we already found our torque net to be negative 0.04, and we just leave it in negative because that's how we were solving in our initial equation. And this is the inertia of center of mass equation for a disk. It's found right here. Just make sure you don't get those confused. They usually will give them to you on every question. If not, you definitely have a sheet that says what it is. So I would not worry about having to memorize those values. So that's over, and then your M is 1, right? And your R is 0.1 squared. So that is going to give you an answer of -8 radians per second. So this is rotating clockwise. So I guess they've made clockwise, it's not -8. It is just 8 radians per second. And because it's positive, it is rotating clockwise. There we go. Determine how many revolutions, determine the angular speed of the disk. Again, you just plug in your angular formula, which is that your initial, so now we're like, so at a time, 2.5 seconds. So we're assuming that it is going to have that rotational speed, which we already found, which is going to be -8 radians per second. And then plus, again, we find your alpha. Oh, sorry. I explained that wrong. That is not your initial. So your initial is going to be 0, right? Because when it's your initial, from what you started with, from up top is 0 rotational velocity, or angular speed, I guess. So then what you're going to do is plug in your alpha, which is that -8 radians per second. And then you're going to multiply it by that time, which luckily we know is 2.5 seconds. Man, that is a tough one. 2.5. So you plug that in, and that is your answer for you. Also, yeah, that's this plus, by the way. That is your answer for you, and it comes out to negative 20 radians per second. But again, like you don't really have like negative angular speed, so you can just write the answer as positive. All right. So then last one for a point. Okay, I am going to scroll, so I'm going to clear drawings. There we go. And scroll down. So for a point on the edge of t equals 2.5 seconds, determine the tangential and radial acceleration. So again, these are just equations in your sheet. Tangential equals alpha r, and then your radial equals dr squared over r, which equals w squared r. Which equals, and then we'll just do this one first. Again, you know your alpha is -8. You know your r is 0.1, and you know that gives you 0.8. So that is your answer for this, and that is in meters per second squared. And you know your W, you know your R, so you plug in your W, which is 20, and you plug in that squared, and then you plug in your 0.1. And that gives you 40 meters per second squared. Cool. All right, so screenshot that if you want. I'm going to move on. So let's go down here. All right, so again for this, I'm not going to walk you through all these because I think this is actually stuff you can do on yourself. I will give you the equation to start out with. So basically it's asking determine the rotation and inertia of the disk cockroach system before the cockroach moves. So it's the same concept we've had, but we just need to add the two rotational inertias. Okay, I probably will end up walking through this a little bit with you, but I do want you to kind of do that middle calculation phase. Cockroach, that's cockroach. So the eye of the disk plus the eye of the cockroach. So then, yeah, again, it gives you the eye of the disk right here. So that is going to equal 1/2 6m, because again, the disk mass is 6m, as you can see up here. And the radius is just big R, so then that's going to be 6mr squared, plus the mass of the cockroach, which is not given to you. It just says, where does it say that? The cockroach has a radius of whatever, but it never mentions like the mass for it. So you just do mr squared, which is because the cockroach does not have any. Okay. The cockroach rotational inertia is just going to be m 0.5 mr squared, and that is from this as well. R squared. So then you solve it, and you should be getting 3.25 m r squared. So yeah, please get from here to here. I have faith that you guys can do that, and when you have questions, Teams us or come to the review on Thursday. Okay, so determine the rotational inertia of the disk cockroach system when the cockroach is on the rim. So now it is no longer in the center. It is on the rim. So we do IF, the final. So then we do the I disk. Plus the IFC, which is cockroach. And this is going to equal, again, it's going to be this. So the disk has not changed. So it's going to be 6m r squared. The disk is still producing the same. And then now this is going to be m r squared. Because so this 0.5, that's where it initially is half the radius. So that's why up here, you do 0.5. That's what that tells you right there. So now it's moved out though. So we have the full radius of the disk that it's impacting this part of the equation. So you just do one, again, solve it, and this should give you 4 mr squared. That's a period right here, or a dot. So yeah. Okay, so then yeah, so if that makes sense, the disk is spinning, the cockroach is right here, comparative to disk, like the disk is like spinning like this or spinning like this, and the cockroach is halfway from the center to the end. So then it moves the end, so then you add in the full R instead of just factoring in the half R in the equation. I am going to scroll down. All right. Last part, determine the speed when the cockroach is on the rim. So again, it's the same thing we've been doing, just in a little different format. You have your I, or your inertia initial equals the Joby initial. So again, your final inertia times your final angular speed is going to equal your initial inertia times your initial angular speed. So we are solving for that angular speed of f because it's on the rim now. It's the final one. And so you get your, and I'm sorry, I told you I would let you solve these, but I hope you're pausing and trying to solve these and then going back and seeing if you're correct. And if you get stuck, totally fine, but I would just say, like, just give it a try. 5 minutes go by, 10 minutes go by, you can't do anything, then you can just look and see what you did wrong. And this should help. So we know our I initial from that first answer of the equation. We know our I final, and our W initial is 1.5. All right, and that comes from, if you look up, I don't want to scroll because I don't want to lose my place. That comes from, or I guess you can. If you go up, it's right here under this, right here at the start. Axis is regular speed is 1.5 radians per second. So we do that. So then we plug in 1.5 and let me finish. Let's see, and then so we literally just multiply these values and we get 1.22 radians per second. All right, cool. All right, so let me know what questions you have. I'll be on Teams. You can look up the schedule for my office hour, or not office hours, just my tutoring hours. I tutor Monday, Tuesday, Wednesday, Thursday. I just don't tutor Friday. And then again, we have that review on Thursday. So please show up to that. I think it'll be greatly beneficial. And I think we went over pretty much everything. Yeah, I think we actually did all of this. So there you go. And again, like I know I don't want to sound like a drag, be like, oh, like do it yourself, but really if you pause it, just think through it on your own before you do it. It takes some willpower, but it's going to serve you a lot better because on the test, these are not going to be the exact at all exactly the questions you get. So if you can understand why you're doing it, you can set it up on your own. That's basically half the point is understanding, setting up, and then that calculation. If you miss that calculation, that is only like 2 of the 11 points at the very end. So I would definitely say focus on understanding the process, thinking through things, being able to describe why you set it up this way to yourself, because if you can clearly set it up on a test and at least get those equations down, you're going to get a lot of points, and that is probably the majority of the points. And then all of those final answers are only worth like 2 of like whatever many points. So like for this one example, just getting that final answer is probably going to only be like 2, maybe 3 of the points out of all of the 11. So take your time learning this, get familiar with these type of questions, understand what you have to put in the equation, and I think you guys will do awesome on this test. Again, message me on Teams if you have any questions. I'm going to stop sharing here. And yeah, good luck on the test, and I hope to see you guys Thursday. So have a great day.